Something that's taught for a long while in your high school life during maths is something called simultaneous equations. You guys probably already know what it pretty much means. It's essentially when we have multiple equations and we want to find essentially the intersection between them, we use simultaneous equations. It's essentially when these two equations are equal to each other, okay? Now, from a graphical perspective, simultaneous equations finds the actual intersection for you. So let's say if we have let's say this line here, we'll focus on linear equations for now. Let's say we have this line here and we have a secondary line there, and they have two equations. If you solve the simultaneous equation between these two, essentially you're just finding where the two equations are equal to each other, and that's essentially where the x and the y coordinate are both equal to each other in that case. So that's what simultaneous equations is doing from a graphical perspective, but from sorry, I'm just gonna rub this out for a sec. Oh, that's kind of dirty. I'll just explain it as I'm erasing this. What I was going to say was when you look at simultaneous equations from an algebraic perspective, it's essentially when you have just an x and y coordinate system, it's where the x and the y both correspond to the same on both of these equations. So for example, if you substitute in x equals 1 to both of these equations, you actually get different numbers. So let's say x is equal to 1, you substitute into the first equation, you get y is equal to 3. If you substitute x equals 1 into this equation, you get 2 minus 5, which is negative 3. So the x and y's don't match up for that specific coordinate, so that's not the solution to the simultaneous equation. So the solution would just be an x and y pair that matches up for both equations. Now, and from a graphical perspective, that's a coordinate, so that's why we consider that as the graphical interpretation of what simultaneous equations are doing. Now, there's two main methods for solving simultaneous equations, algebraically in VCE methods. Now, I've got two examples here, and the reason why I have two examples is because these different examples kind of call for different methods. So the two methods are substitution and then also elimination. Now, sometimes it's better to use one, and sometimes it's better to use the other one. But there's always one that's more advantageous in some situations. So we'll go through these two examples, and we'll just explain why one way is better than one, and one way is better than the other for these two sets of equations. Now in this first situation, we have y is equal to x plus 2, and then we also have y is equal to 2x minus 5, and we're asked to solve these equations simultaneously. Now, because we have y is equal to something, and then y is equal to something else, the way that we use for this set is substitution. I forgot the word for it for a second. Substitution for this set. Now, how do we structure our working out for substitution? What we do is, for any simultaneous equation problem, we label our equations, so just 1 and 2 in this case. Now, because I have y is equal to something and y is equal to something else, what I can do is I can just simply say equation 1 is equal to equation 2. So equation 1 is equal to equation 2. And why I'm allowed to do that is because it's already in this form where you have y is equal to some sort of expression. So what I can do is I can make the two expressions actually equal to each other. So what I've done is I've done the right expression, or the right side of the equation 1 is equal to the right side of the equation 2. And the only reason why I can do that is because these y's should be the same, because we're trying to solve them simultaneously. So then I'm just left with these x expressions here, and I just rearrange for x. So I can move this to that side by minusing it, and I'll move the constant to the opposite side. So I end up getting 2 minus negative 5. I'm just doing the long way here. You don't have to do as many steps as me, but I'm just kind of trying to emphasize, where I get all of my numbers from. So I've moved the x to that side, I've moved the minus 5 to that side, so I end up getting 7 is equal to 2x minus x, which is just equal to x. Nice. Now, x is equal to 7, I just substitute this x is equal to 7 into either one of my equations, and I should get the same answer regardless of which one I substituted in. And that's the whole point of simultaneous equations. It's that the corresponding x value will equal the y value for any one of my equations. So it doesn't actually matter which one I substituted in. I'm just going to substitute it into equation 1 because it seems a bit simpler to calculate. Therefore, y is equal to 7 plus 2, which is equal to 9. Therefore, my final solution, just in coordinate form, just to make it simpler, is 7, 9. Essentially, x is equal to 7, y is equal to 9. Nice. Now, this is the substitution method, and it worked the best because we had y is equal to something and y is equal to something else. But just in general, if you ever have something where you can, or a set of equations where you could substitute something directly in, then the substitution method works better. Another example that doesn't look exactly like this, but kind of this is kind of the same deal. If you have y is equal to x plus 2, we'll use that same equation, but then we had 2x plus y is equal to 5. So it kind of looks similar. We have one equation where it's y is equal to x plus 2. The other one is 2x plus y is equal to 5. What you can do is you can substitute this equation into that y there. So you can actually do this as substitution as well. It doesn't have to be y is equal to something and y is equal to something else. We have this y isolated over here, and I'll just substitute that expression x plus 2 into that y spot. So you can kind of do the same setup for with substitution method for other things where you have a variable isolated. So that's usually the most common case where I would use substitution method, just if you want kind of a formulaic way of applying it. It's just whenever you have a variable isolated and you can just substitute that expression into the other equation to solve your equation simultaneously. Nice. Now, this set of equations here most likely calls for the elimination method, which is the second method of solving equations simultaneously. Now, we can solve this using substitution as well, but it's not directly. So in the form that it's in, elimination method is better, but you can do rearrangement to get it into a form that's similar to this or similar to the red one that I wrote before, and you get the same answer. But we just use elimination method just to show how to actually do it. What we have is we have kind of something x plus something y is equal to a constant, something x plus something y is equal to another constant. And the goal of elimination method is to eliminate one of your variables. In this case, it's going to be x or y. And we just have to think about which one is easier to eliminate. Now, how we eliminate equations is we usually add them or subtract them from each other. So the goal of this elimination method is to either make the x variables or the x number the same, like the magnitude outside of the x, the coefficient, or the magnitude of y, the coefficient of y, the same. Now, what I'm going to do is I'm just going to make the coefficient of x the same, and the reason for that is I can multiply equation 2 by 2, and then what happens is this becomes 2x here. Now I have 2x there, 2x here, then I'm able to eliminate them. So I kind of show you how that looks. If I do 2x plus 4y is equal to 2, I'm essentially multiplying both sides of the equation by 2, which still keeps it balanced. I'm just going to call this equation 3, just a new equation because it's different from equation 2. Even though mathematically it's the same, I just want to label it something differently just so I can be clear with my working out. Now what I can do then is I could say equation 3 minus equation 1, because then what will happen is that the x variables or the x terms cancel out. So if I say equation 3 minus equation 1, I just take the left side of equation 3, so that'll be 2x plus 4y, that's the left side of equation 3, and I minus the left side of equation 1, 2x plus 3y, I'm minusing that whole side. And then I just minus the right sides as well. So this is all equal to 2 minus 6. Just make sure that you keep your sides or what you're minusing consistent. So then the x terms will cancel out. So I'm left with 4y minus 3y. So I'll just write this all out just to make it clear. Is equal to 2 minus 6, which is negative 4. 4y minus 3y is equal to 1y. So y is equal to negative 4. Nice. Cool. So now we know the y term. Then we can just substitute that into any one of our equations to find our x term. So I'm just going to substitute it into equation 2. And the reason for that is because you've just got the x term there, so I just have to minus the 2y across. So we end up getting x plus 2 multiplied by negative 4 is equal to 1. Therefore, x is equal to 1. This whole term will be negative 8, so it would end up being plus 8 to move that to the other side. So that's equal to 9. Therefore, my final solution is just 9, which is the x term, comma negative 4, which is the y term. Nice. So this is the elimination method. So essentially, just as a summary, I just wanted to eliminate one of my variables. So I make the coefficient of them the same, and then I could just minus the equations from each other. Now, what you could also do is if this equation here ended up being 2x, what you can do is instead of minusing the equations from each other, you can just add them instead. Because if you go 2x minus 2x by itself, that's going to equal 0 because it's going to cancel out. So you can also add your equation depending on your needs. Obviously, there's a lot of different combinations of what you can do. And you don't only have to multiply one equation, you could also multiply both if that's necessary. In this case, it wasn't necessary because if I just multiplied this, this second equation by 2, I end up getting 2x. But let's say if I wanted to make the y's the same for whatever reason, it's not as efficient, but it's still fine. What you can do is I can multiply this equation by 3, and then this equation by 2. And then what happens is that the 3y becomes 6y, and then this 2y multiplies by 3 to become 6y, and then these two are balanced, so they'll actually cancel out. But as I said, it's not that efficient in this case, because what I can do is I could just multiply the second equation by 2 to make the x terms the same. Now, a lot of people might not actually think about this, but whenever we're solving simultaneous equations, we just assume that there's going to be an answer. And that's because the question is asking us for a solution. But this is actually not always the case. In most cases, yes, there is one solution, or there are multiple solutions. And that case looks something like this. It's where we're focusing on linear equations, by the way, for now. But let's say one line looks like this, and then the other line, I'll use a different color. It looks something like that. Now, if you look at these two linear equations, you can see that there's one visible intersection between the two, okay? And this is what happens most of the time. So in the previous part of this video, we used two different methods to solve two sets of simultaneous equations, and both of them came up with one solution. So this is what they will look like on a Cartesian plane if you sketch them out. Something like this, where you have two lines and they have one intersection. Now, what we never think about is, are there any cases outside of this? And if there are, what conditions are there to make this happen? And what other conditions are there to make the other cases happen? So first, let's just talk about this case, and then we'll just expand that to other types of cases that we may have whenever we're solving simultaneous equations. So what you can see in this case is that you have two lines and they're non-parallel. So what that means is that they're on different slopes, and slopes in linear equations are represented by the gradient, or m. So what I'm going to do is I'm going to say that for this one intersection to exist, your gradients just can't be the same to make them non-parallel. So I'll say m1 is not equal to m2. I'm just going to specify in brackets that it's because you want two lines that are not parallel. Now in this situation, you're going to have only one intersection. Okay, now m1 is not equal to m2, so pretty much it could just be any other value as long as it's not the same. Now let's talk about the second case. What if they are parallel? What actually happens? So a lot of you, when you would think of parallel lines, you're just going to think of two lines that are separate that look something like this. So one line's like that, and then the other line is something like that. So you can see visibly they're parallel, and if two lines are parallel, they essentially never meet. Okay, so in this case, they're kind of separate, and because they're on the same slope, they'll actually never meet. So in this case, I'm actually just going to specify that this gives us one solution. So that's the key here. This gives us one solution or one intersection. In this case, it's going to give us 0 solutions, or 0 intersections if you're looking at the Cartesian plane. Now, what conditions are there to get 0 solutions? The first one is going to be that they're parallel lines, so m1 is going to equal m2, or pretty much the gradient of one is going to equal the gradient of the other. So I'm just going to say this causes parallel lines. Now, one other condition that a lot of people might not think about is the fact that if you have parallel lines, they can either be separate like this, or they can actually be lying on top of each other. Now, when we have a linear equation, how do we represent kind of like the height or where it sits? The m represents the slope, but our other variable, which is the c, or the y-intercept, that kind of represents how far up our equation is. So what we don't want to happen is we don't want the equations sitting on top of each other, because that actually won't give us 0 solutions. That's going to give us infinite solutions, which is actually our third case, which we'll talk about after. It's pretty similar to 0 solutions. But what we need to think about is, if we don't want the equations lying on top of each other, then you just don't want your c value to be the same. So not only is m1 equal to m2, but c1 cannot equal c2. And that's just to make sure that the lines aren't at the same height, or essentially not at the same y-intercept. Now, in that case, what would that actually look like is our third case, if they were equal to each other. It's like one equation's like this, and then the other one is lying right on top of it, sorry. I'm just trying to draw them as close together as possible because I don't want to mess up the ink. But yeah, that's what that would look like. It's essentially just two lines lying on top of each other, and that's why we think of it as infinitely many solutions, because like you can imagine, if every x and y coordinate on this line is a potential solution, because they're all corresponding intersections. So what we want in this case is we not only want parallel lines, m1 is equal to m2, but we actually want c1 equal to c2 as well, to make them the same height. And if you actually imagine this, it's kind of interesting. If you have y is equal to mx plus c, and if your m is the same, and your c is the same, you essentially have the same equation. So it's actually, when you have this red and blue line that are lying on top of each other, you can think of it algebraically, but also conceptually as well as the same equation. So these are pretty much our different cases, and a lot of the times in VC methods you might get this case. Most likely you will get this case if a question's asking you for to find the intersection or intersections between two lines, but you potentially could get these cases as well. So if you do get unusual solutions, it might not be that you did something wrong, it could be that one of these two cases is popping up, and we'll talk about that in the next part of this video. Now, not only is it important to know our different types of simultaneous equations and what can actually happen when we do have different cases, but what does that actually look like algebraically when we try and solve equations and we might not know which one of the three cases we're falling in. So I'm just going to go through a couple of examples for these two cases here, which are the more peculiar ones. We went through the one solution cases before, and it's pretty self-explanatory. If you have one solution for a set of linear equations, you just expect to get an x and y return, right? But you don't get the same for these cases because, as I said, it's a bit more peculiar, it's a bit more unusual. So we'll just go through a set of examples and we'll see what actually happens for these two cases. So underneath the zero solutions, we have a set of linear equations. Y is equal to 2x minus 1, y is equal to 2x minus 3. And you can see that these conditions are fulfilled where the m is the same, so you have parallel lines, but the y-intercept is actually different. So if we try and solve these two equations together, let's just do some proper working out. We say 1 is equal to 2, therefore 2x minus 1 is equal to 2x minus 3. So what happens is our 2x's cancel out because that's on both sides. So therefore we end up getting -1 is equal to -3. Now a lot of people would see that and think, oh, have I done something wrong? Like, how have I got something is equal to something else? That's incorrect. Obviously this is an incorrect statement, right? Now what this actually means, it doesn't necessarily mean that you did something wrong. A lot of times it does, but it might just be that you did a mistake. But let's say if you get this legitimately and you can't see any mistakes, what this actually implies is that you have no solution to an equation. Now that actually might be intentional. In this case, I've constructed this problem specifically to make it intentional. So whenever you get something is equal to something else and it's incorrect, the statement, then it usually means that you either made a mistake or there's no solution to whatever you're trying to find. Okay? Now, it might be the same if you have the square root of a negative number, because in VC methods, we don't have imaginary numbers or complex numbers. So in this case, what's actually happening is that we're just saying that we have no solution to our equation. So that's completely fine, because in this case, it's actually intentional. So if you get this result and you're kind of confused, just think about, am I expecting no solution in this case? And you might look at your equations and check the conditions and say, okay, that actually makes sense that I have no solution. So that's what happens when you try and solve this equation here. Let's try and do the same here. Let's try and actually solve this equation and see what the result is. So we have 1 and 2. So in this case, what I might do is I might substitute equation 2 into the first equation. So I just say 2 arrow 1, just to imply that I'm substituting it in. So I get 2y is equal to 4. Actually, no, sorry, did that wrong. Let's get rid of this. So what I'm going to do is I'm going to replace y with 2x minus 1 in my first equation. So I get 2 outside of 2x plus 1 is equal to 4x plus 2. If I expand these brackets here, I get 4x plus 2 is equal to 4x plus 2. Now I could cancel out the 4x's on both sides, and what I'm left with is 2 is equal to 2. Okay, again, kind of confusing. If you got this result when you're trying to solve for x, you might be thinking, oh, what's happening here? Now, what's actually happening is we have 2 is equal to 2, which is actually a correct statement, which is different to this one. This one was an incorrect statement, but this one's actually a correct one. And they actually mean different things algebraically. When you have 2 is equal to 2, or you have some sort of correct statement, a lot of the times people would have 0 is equal to 0, or 1 is equal to 1. What that implies is that you have infinitely many solutions. Now you might be thinking, oh, how do you get infinitely many solutions from this one, but then no solutions from this one? So because this is a correct statement, it's implying that every single x and y value are the same. You don't have to really think about why, maybe you can just accept it. And there's probably more detailed explanation than what I'm giving you at the moment. But just think about if you have a correct statement, it's implying that it's always your equation or what you're trying to solve for is always true. Now in this case, what's happening is because you have infinitely many solutions, it doesn't matter what x and y pair you have, it's always going to be true. So that's why the 2 is equal to 2 is implying that, yes, 2 is equal to 2, but it's if you think about it more deeply, it's getting pretty deep right now, but if you think about it more deeply, it's implying that whatever set of x and y values you have is true, the same as this statement here, 2 is equal to 2. It's true. I'm just going to say that. Always true. Always. So that's what's implying with infinitely many solutions. When you have an incorrect statement, so this is actually false, -1 is equal to -3 is false, the way I take that is it's always false. So no matter what x and y pair you have, you're never going to find a solution, because that's what this statement is kind of implying here. Because you tried to solve for x and you couldn't, and you got a false statement, therefore it's implying that you have no solution. That's essentially implying that this set of linear equations is always going to be false. There's never going to be a solution pair that matches with it. You don't really have to understand that. I'm teaching you, I'm trying to explain that based on knowledge that I've learned throughout engineering, because that's what that's what I study, that's what I've majored in. And we've kind of learnt about this through learning a bit more maths, a bit more deeply. You don't really have to understand that, but it's good to know that if you get those results, it's not necessarily that you did something wrong. It means that there's a deeper meaning behind it, and this is my best explanation to try and get there. But yeah, the best thing to do is kind of note down these certain cases where you might get 0 solutions. So you see my gradients the same. So that's how you know you're going to get either 0 solutions or infinitely many solutions. This one is a bit more hidden, where if you look deeply, equation 1, is just the same as equation 2. It's just multiplied by 2 on both sides. So these equations are essentially the same algebraically. These equations are not the same algebraically, but they're parallel. So if you look out for those key features, then you shouldn't have a problem with getting these algebraic results. But if you do, just note that there might be a deeper meaning behind it. So here's an example of a complex problem where we have 2 simultaneous equations, but we have a parameter, and we're asked to determine the possible values of a parameter for, in this case, just one solution between our equations. So let's have a read of this question. Determine when the 2 equations mx plus y is equal to 2 and 2x plus m minus 1y is equal to -4 has one solution. So what we need to do is think about when one solution actually occurs and see what possible values of m that's actually happening for in this specific case. Now, as I said in the previous part of this video, it's really important to note that the m and the c in both of our equations, in whatever example that we have, they're the key parts. So what we need to do is we need to rearrange both of our equations to be y is equal to mx plus c, or just in that form. So what I'm going to do is I'm going to take each equation separately and rearrange it. So we'll start off with mx plus y is equal to 2. It's pretty easy how to rearrange this one. We just move the mx to the other side. So we say y is equal to -mx plus 2, just like that. Now for the second equation, it's a bit more complicated, so I'm just going to rewrite it first. 2x plus m minus 1y is equal to -4. The first thing that I'm going to do is I'm just going to move the 2x across to the other side. So I end up getting m minus 1y is equal to -2x minus 4. And then I'm going to divide both sides by m minus 1. So therefore, y is equal to -2 over m minus 1, x, and then minus 4 over m minus 1. Perfect. Now what we can see is that both of our equations, it's a bit messy here, so I might just square them. So both of our equations are now in the form y is equal to mx plus c. Now, for one solution, we have to remember that one solution means that we have non-parallel lines, which means that our gradients are going to be not equal to each other. So we can see that both of our coefficients of x involve m. So what we need to do is just say that those two gradients just shouldn't equal each other, but m can pretty much be any other value. So what we need to do is say, okay, we take the m from this equation. So I'm just going to say in general, this is a statement that we should always use just to show what our working out is actually doing. We just say m1 is not equal to m2 for one solution. And then I just take those m values from each of our equations. So what we say is that -m, which is from the first equation, is not equal to -2 over m minus 1. And then what we simply do is we treat this as a normal equation, just pretend it's a normal equation without that slash through the equal sign, and we just find the possible values of m. But they're actually going to be the values that we can't have, but we can have any other value. Sweet. So what we need to do is now just multiply the m to the other side, or sorry, m minus 1 to the other side. So we get -m outside of m minus 1 is equal to negative 2, sorry, not equal to negative 2. I've got a negative on both sides, which I'll just cancel out. So I end up getting m squared, if I expand this bracket, minus m is equal to 2. Oh, sorry, not equal to 2. Now, I can just solve this equation for m. So m squared minus m minus 2, not equal to 0. And I just factorize it from here. M minus 2, m plus 1 is not equal to 0. I'm just going to take this back up here. Therefore, m cannot equal 2 or negative 1. This is just normal quadratic solving if you're unsure of this method. So these are the two m values that I can't have for one solution. Nice, sweet. One thing we also have to consider is, I just noticed this now as well, we see that in our equation, we actually have m minus 1 on the denominator. Now that can actually cause some problems, because let's say if m is equal to 1, what actually happens with this equation, if we look at our original, we could look at the original form, or we could look at this form as well, is that if m is equal to 1, what actually happens is you're dividing by 0 in this case, which is actually problematic. But we'll actually come back to that once we get the solution from this part here. So m is not equal to 2 or negative 1, but m can pretty much be any other value. So we say, therefore, m is an element of all real numbers excluding 2 and negative 1. I didn't do that in ascending order, but it doesn't really matter. So these are the possible values of m that we can have for one solution. We're essentially saying that m can be any other value except negative 1 or 2, because that causes issues with the gradients being the same. Nice. Now, as I was saying before, the m is equal to 1 can actually cause some issues, so we just have to double check that that's a problem or not. So what we have here is we'll just go to our original forms. Let's say if m is equal to 1, and the reason why I'm just concerned about that is because we're dividing by 1 in this form here. But that actually doesn't mean that it's an issue, because we rearranged it to go into that form. So what I'm going to do is I'm just going to substitute m is equal to 1 into our original forms, which are here and here, and then see what actually happens. So if m is equal to 1, what happens to this equation is we get x plus y is equal to 2. There's no problems with that equation, that's perfectly fine. Now with this equation here, it's a bit more of a mystery, because if m is equal to 1, this term actually becomes 0. So we actually end up getting 2x is equal to negative 4, which means that x is equal to negative 2. Now that's actually not an issue, it's just not in our standard form y is equal to mx plus c. X is equal to negative 2 is pretty much just a horizontal line at x is equal to negative 2 like that. So that's what that line is going to look like. And x plus y is equal to 2 is just going to be a normal linear equation. So that's actually just going to have one solution there. So the reason why I bring this up is, even though this equation actually ends up becoming a horizontal equation, if you have it as m is equal to 1, that's actually not a problem, because it still causes one solution, so it still fulfills our condition. So there's actually no issue with the solution that we've produced, we just leave it as it is. But the reason why I bring it up is just to keep in mind that if you have these key, I guess what you'd say is m is equal to 1 is kind of a key point where you do have some sort of outlier compared to what's expected, because you are producing a horizontal line. But in this case, it doesn't cause any issue just based on checking with substitution. Therefore, we're good to go, and this is our final solution. So in that part, we just found the valid values of m to get one solution. Now we're just going to find the values of m to get no solution between our two equations. As per the previous part of this video, if we want no solutions, we want parallel lines, but different y-intercepts. So essentially what we want is that we want m1 to equal m2 for parallel lines, but then we say c1 is not equal to c2. Now, for m1 equal to m2, we pretty much solved that before. We just did it with the inequality symbol, but essentially the solutions to that, m1 is equal to m2. I was going to say, I'm pretty sure m was an element of all real numbers excluding negative 1 and 2, I believe. Yes, I think that's right. So that's what we got from solving that m part before. We actually don't need to do it again because we just did it in the previous part. So you'll notice that whenever you do more and more parts to these types of questions, it actually becomes a lot easier because you're recycling a lot of work. Now for C1 not equal to C2, that's something that we still have to solve for because we didn't do that previously, because for one solution, it actually doesn't matter what the y-intercept is. It just matters that the lines are non-parallel. So for C1, so I'm just going to say for C1 not equal to C2, what's going to happen is we say 2 is not equal to negative 4 over m minus 1. And we essentially just solve for m, and we see if there's any issue with this. I actually realized I made a mistake, just really quickly. This was the solution for m1 not equaling m2. So if I want m1 to equal m2, I just take my exceptions that are here. I'm just taking like the opposite of what I took before. So in this case, m is just going to equal negative 1 or 2. Yeah, that makes more sense. Now for C1 not equal to C2, I just solve this equation here. 2 is not equal to negative 4 over m minus 1. Therefore, 2m minus 2 is not equal to negative 4. Bring the 2 to the other side, so I get 2m is not equal to negative 2. Therefore, m cannot equal negative 1. Now, this example is constructed on purpose because, as you can see, m is not equal to negative 1 is one of our conditions to get no solution. But that actually contradicts with this one, which says that m should equal negative 1. But what we need is we need both of the conditions. I'm just going to say both conditions need to be fulfilled. Now, the reason why that's important is because if this condition says that m is equal to negative 1 is fine, but this one says m is equal to negative 1 is not fine, then we actually can't take m is equal to negative 1 anymore, because as I said, both conditions need to be true. So therefore, for no solution to exist, it's only when m is equal to 2, because m is equal to 2 corresponds to this condition here, where the lines are parallel, but it also corresponds to this condition here that says that m cannot equal negative 1, because our y-intercepts have to be different. So this part's the most basic one. If we want infinite solutions, we need the gradients to be the same and the y-intercepts to be the same. So m1 must equal m2, and C1 must equal C2. Now we actually solved these conditions both in previous parts, so that's why this one actually becomes the most easiest one. So m1 is equal to m2 gave us solutions of m is equal to negative 1 or 2. When we solved C1 is equal to C2, we didn't do this exactly. Again, we solved the non-equality, but essentially what we got from that one was that m should be equal to negative 1. Now in this case, because we need both conditions to be true, the only one that corresponds to both is m is equal to negative 1. So therefore, for infinite solutions, or essentially to get both lines being the same, but we call that infinite solutions in this case, we need m to equal negative 1 as our only answer.